PCA. Principal Component Analysis. PCA. In Machine Learning. AI Intermediate Level. Introduction. Modern datasets often contain many features. Dimensions. For example, image datasets may contain thousands of pixel features. Text datasets may contain thousands of word features. Financial datasets may contain many indicators. When datasets have too many features, machine learning models may suffer from slow training, increased computational cost, risk of overfitting, difficulty visualizing the data. To address these problems, machine learning uses dimensionality reduction techniques. One of the most popular dimensionality reduction techniques is principal component analysis. PCA. PCA transforms a dataset into a smaller number of variables while preserving most of the important information. PCA is widely used in image processing, data visualization, pattern recognition, financial analytics, bioinformatics. Understanding PCA helps learners build efficient machine learning models and simplify complex datasets. What is PCA? Principal Component Analysis. PCA is a dimensionality reduction technique that transforms a dataset into a new set of variables called principal components. In simple words, PCA equals transforming data into fewer dimensions while keeping the most important information. Example concept. High-dimensional data means PCA means reduced dimensions. The new features, principal components, capture the maximum variance in the data. What are principal components? Principal components are new variables created by combining the original features. Example concept. Original features means linear combinations means principal components. Each principal component captures a portion of the dataset variance, is independent from other components, represents a direction of maximum variance. The first component captures the most variance. The second captures the next most. And so on. How PCA works. PCA transforms the dataset by identifying directions that capture the most variance. Example concept. Dataset means identify directions of maximum variance. Steps involved. Standardize the dataset. Compute the covariance matrix. Calculate eigenvectors and eigenvalues. Select principal components. Transform the dataset into reduced dimensions. These steps allow PCA to represent data using fewer variables. Variance in PCA. Variance measures how spread out the data is. PCA attempts to keep the directions that explain the largest amount of variance. Example concept. Higher variance means more important component. By preserving variance, PCA keeps the most important information in the dataset. Eigenvalues and eigenvectors. PCA uses eigenvectors and eigenvalues from the covariance matrix. Example concept. Covariance matrix means eigenvectors means principal components. Eigenvectors represent directions of maximum variance. Eigenvalues represent the amount of variance captured. Principal components are selected based on largest eigenvalues. Dimensionality reduction with PCA. PCA reduces the number of features while preserving important information. Example concept. 100 features means PCA means 10 principal components. The reduced dataset contains fewer variables but still captures most of the original data variance. Example of PCA. Example dataset. Feature 1, Feature 2, Feature 3. Data point 1. Data point 2. After PCA. PC1, PC2. Reduced representation. Example concept. Original features means transformed principal components. The new features represent the data in a simplified form. Choosing number of components. In PCA, developers choose how many principal components to keep. Example concept. Total variance explained means choose number of components. A common approach is to keep components that explain 90 to 95% of total variance. This ensures minimal information loss. PCA for data visualization. PCA is often used to visualize high-dimensional data in 2D or 3D space. Example concept. High-dimensional data means PCA means 2D visualization. This helps analysts understand patterns and clusters in the data. PCA workflow. A typical PCA workflow looks like this. Dataset. Down-pointing arrow. Standardize features. Down-pointing arrow. Apply PCA. Down-pointing arrow. Select principal components. Down-pointing arrow. Reduced dataset. Down-pointing arrow. Train machine learning model. This workflow simplifies datasets before training models. Advantages of PCA. PCA provides several benefits. Advantages include: reduces dataset dimensionality, improves training speed, reduces risk of overfitting, removes feature redundancy, helps visualize complex datasets. Example concept. Reduced dimensions means faster and simpler models. These benefits make PCA widely used in machine learning. Limitations of PCA. Despite its advantages, PCA has some limitations. Limitations include: loss of interpretability of original features, potential loss of information, assumes linear relationships between features. Example concept. Feature transformation means harder interpretation. Therefore, PCA must be used carefully depending on the application. Example Python code. PCA can be implemented using scikit-learn. Import PCA from sklearn. Decomposition import PCA. Apply PCA. PCA equals PCA. N underscore components equals 2. X underscore reduced equals PCA dot fit underscore transform. X. This reduces the dataset to 2 principal components. Real-world applications. PCA is widely used in AI systems. Image processing. Reducing image feature dimensions. Finance. Analyzing financial indicators. Bioinformatics. Analyzing genetic data. Data visualization. Visualizing complex datasets. Natural language processing. Reducing dimensionality of word embeddings. Concepts learned from PCA. Understanding PCA helps learners understand. Checkmark how dimensionality reduction works. Checkmark how variance explains data importance. Checkmark how eigenvalues and eigenvectors are used. Checkmark how high-dimensional datasets are simplified. Checkmark how machine learning models become more efficient. PCA is one of the most important techniques in machine learning and data science. Simple definition. Principal component analysis. PCA. A dimensionality reduction technique that transforms data into a smaller set of variables called principal components while preserving most of the dataset variance. Final summary. Principal component analysis. PCA is a widely used dimensionality reduction technique in machine learning. It transforms high-dimensional datasets into a smaller set of principal components that capture the most important information. By reducing the number of features while preserving variance, PCA improves model efficiency, reduces computational cost, and helps visualize complex datasets. Understanding PCA is essential for working with high-dimensional data in machine learning and artificial intelligence systems.